in the previous lecture we had seen how to do a quadratic or p equal to 2 approximation. So we had defined the global basis functions which were quadratic in nature, piecewise quadratic in nature with a local support, and then we went ahead and in an element talked about the quadratic shape functions in the element. Piecing together these shape functions, we got or patching them up, we got the global basis functions, as we had seen through the drawings in the previous lecture. Now obviously we should ask the question, why do we need to do a quadratic approximation when the linear approximation seem to be doing a good job? So let us see this thing through a simple example. So this is my domain. Let the exact solution to the problem do something like this. Okay. Now for this exact solution, we are going to make, so for this domain, let us make a 2-element mesh. This is my point x1, x2, x3. Now, if I did a linear approximation using the differential equation that we had defined, then my solution should be, as we had seen, should give us the exact solution at the nodes. So, we should get a figure like this. Now the question is, for the same mesh that is fixing my x1 and x2 and x3, can I improve the solution? So what should I do to improve the solution fixing the mesh? So one simple thing I can do is, I can take a quadratic approximation. If I take a quadratic approximation, what most possibly will happen is this, that the nodal value will be exact again, and then from here the quadratic may do something like this. So if this was my linear, possibly this is going to be my quadratic. And this is obvious that the solution to the approximate problem will be closer to the exact solution if I took, for the fixed mesh, a higher order approximation piecewise. If I went and did now a higher than p equal to 2 approximation, so what will be the next thing that we can do? We can talk of a cubic approximation. So let us do the cubic approximation. Or we said that the order of approximation is 3 and is defined by the value of p. So when I do the cubic approximation, so let me take it through a simple 2-element mesh. So when it's a cubic in an element, that is piecewise it's a cubic, we know that we can define a cubic using 4 independent functions. Okay. So we need to have, because we have to have linear independence and completeness for our basis functions, we need to have in an element 4 such functions. So let us not bother about that now, let us draw. How will I draw? This will be my point x1, this will be x2, x3, x4, x5, x6 and x7. What I have done is, this is my element I1, this is my element I2, and the extremities of the elements are given by x1, x4 and x4 and x7. Now for each of the elements I have introduced two interior nodes. For the element 1 we have the interior nodes x2 and x3. For element 2 we have two interior nodes x5 and x6, such that they are equally spaced in the element. So if we have a uniform mesh, that is the mesh of the same size everywhere, so the h will be equal to L by 2 in this case. So what is the size of the element, that is the distance between x1 and x4 is h, and between x4 and x7 is h. So the distance between x1 and x2, since these are equally spaced, will be h by 3. So this distance is going to be h by 3. So now for this, let us, through a picture, define a cubic function such that at the point 1, x1, it has a value 1, and at x2, x3 and x4 and all other points it has a value 0. So let me just draw this function. So if I want to draw this function, I can think of a function like this. This will be our phi 1. Similarly, I can draw the function which has a value 1 at the point x2 and 0 at all other points. So what is the cubic function which has value 1 at x2, is 0 at x1, x3, x4? So that cubic function is, if I draw, it will look like this. This is phi 2. Now the function which is 1 at the point x3, 0 at x4, x2 and x1. So that function will be phi 3. And then finally the function which is 1 at the point x4 and 0 at x1, x2, x6. So what I am doing first is I am defining the functions in the first element. Then we will continue to the second element. So this function, at least it should look like this. So this is going to be my part of phi 4. Now this function also is non-zero in this element, so it should do the same job of vanishing at points x5, x6, x7 in the second element. So this is how we are going to define phi 4. Okay. Now if I have to define phi 5, how will I define? Phi 5 has to vanish at x4, x6, x7. So it is going to be, this is phi 5. Similarly, phi 6 will be like this, and phi 7 so this is phi 6 and phi 7. So if I had more elements in the mesh, I could have drawn the shape functions like that, the basis functions. So these are the global basis functions, and as we have been doing till now, let us now look at its restriction to an element. So what we will do from these basis functions, we know that U7 in this case is equal to sigma I is equal to 1 to 7 ui phi I of x. Now I will not carry this upper subscript 7 throughout my presentations from now on. I will switch on to UFE, where UFE will stand for the particular series that we are talking about. Okay. Now, so this is the representation of our finite element solution. So how are we going to do this thing at the element level? So in the element level, we have to define now the element level shape functions. Okay. So this is x1. So if this is my element k, this is x1 of element k, x2 of element k, x3 of element k, x4 of element k. So now at the element level, what is going to be my n1? This is my n1 of element k. n2 of element k, this is n2 of element k. Similarly, what is n3 of element k? n3 of element k will be, it should be 1 at the point x3. So n3 of element k, and similarly I will have the n4 of element k. n4 of element k. So by now it should be obvious what is the functional representation of these ni's. So given these 4 points in the element, the nik is equal to product of j going from 1 to, how many we have points? 4. J is not equal to I, x minus x jk divided by x ik minus x jk. For example, if I am talking of n1, so in n1, in this product we are going to ignore j equal to 1. So we will have x minus x2k into x minus x3k into x minus x4k divided by x1k minus x2k into x1k minus x3k into x1 minus x4k. This is how we are going to define the generic ith shape function of an element which is of degree 3. Okay. So given this definition, now all the shape functions can be defined through this product rule. This is the Lagrangian definition, as we had pointed out earlier. These are called Lagrangian shape functions. When I do this definition of the Lagrangian shape functions, then we have to, you remember that we have to go from the element level definition to the global level definition. So we have to have the local to global numbering. So local to global numbering, how will it be done? Here I will have I is equal to 1, 2, 3, 4. If you check with the mesh that I had drawn, the recipe is very simple. That the element level I for the element k, so we are talking of element ik, is equal to, globally it corresponds to three into k minus 1 plus I. The way we have done the numbering of these points or the nodes that we had placed, okay, it gives us the one-to-one correspondence like this. So the local I will correspond to the global 3 into k minus 1 plus I. You should check that. Next is, what is the element stiffness and load vector contribution to the global system? For that, we are going to go back to our representation of the problem. Here I am going to substitute the finite element solution, and the ith equation, if you remember, comes from f phi I. So this was what we have globally, and as we have done earlier. So let me go back and point out a few more things in terms of terminologies. This n1 of the element and the n4 of the element are, as we had done in the quadratic case, are called the edge or corner shape functions. This n2 and n3, if you see, they are only defined in the interior of the particular element. They are 0 everywhere else, while n1 and n4 are also non-zero in the neighboring element. That's why they are called edge shape functions or vertex shape functions, and n2 and n3 are called internal bubble functions. And if you see that this n2k and n3k is actually the total definition of the global basis function. Okay, so let's come back here. In this expression, what we have, so we would like to get, using this expression, the element level contribution. So we know that at the element level, this will get contributions from phi 3 into k minus 1 plus I plus 1 to phi 3 k minus 1 plus 4. So when we make the element equations, we will have how many element equations? Because of p equal to 3, we have 4 shape functions in the element. We will have 4 equations at the element level. And what are these equations? These equations will be the Kij of the kth element is equal to integral over which node am I going to go from? So I will go from x1 of k to x4 of k Ea d phi, sorry, not phi, let me go in terms of n, dnj of k dx dn I of k dx dx. I am not putting the string, the distributed string part here, it is only for the bar. If you had the string, you will have to add the additional contribution from the string. Okay. Similarly, the fi for the element k is x1 of k to x4 of k f nik dx. I am not adding the boundary part because that will be added through the boundary condition. So this is what I am going to get at the element level. These are going to be my element level equations. Okay, and you see that this one is a 4 by 4 system matrix, and this one is a vector of size 4. Now we have done sufficient amount of assembly to know how to assemble these things. So assembly will do what? So to do the assembly process for the element, we would start off by defining the global stiffness matrix Kij such that it is given a value 0. This is initialized. and similarly we will Fi is equal to 0. Now can you tell me what is the size of this matrix? This global stiffness matrix will have a size, you can see it will be equal to number of elements into 3 plus 1 cross number of elements into 3 plus 1. So it's a matrix of size 3n plus 1. Similarly, Fi is a vector of dimension 3n plus 1. Okay. So then when we got the kth element, what will we do? So we will take the Kij global is equal to Kij global plus Kij of the kth element, where I, let me first do the load vector part also. Fi is equal to Fi plus Fi of the element k. Here I is equal to, as we have done it till now, by now, 3 into k minus 1 plus I, and j is equal to 3 into k minus 1 plus j. So we know which global entries, which global row and column should my element level row and column entry go to or assemble into, and similarly for the load vector. So this is the assembly process. Now the question is, can I generalize it? So can I generalize it to any p order approximation? Nobody tells us that the approximation should be of order 1, 2, 3 or 4. What governs whether I use an approximation of order 1, 2, 3 or even 100 is, first of all, the accuracy of the solution that we desire and also the economy of the computation. So accuracy and economy. These are some of the primary considerations that we have to have. So whatever p order, whatever mesh size gives us the best solution is what we want, and as quickly as possible. So can I generalize what I have done earlier for the p equal to 3 case to an element of order p, a generic element of order p. So a generic element of order p means it should have p plus 1 independent shape functions. Where does this come from? This comes from the completeness, in the sense that we would like to represent a polynomial which is of order p, degree p, exactly using these functions. So a polynomial of degree p will have p plus 1 terms. Okay. Now it will have p plus 1 independent terms, because these monomials 1x and so on up to x to the power p are independent monomials. So when I want to represent it using these shape functions, we need at least p plus 1 shape functions, and that's what we are doing. So we have these p plus 1 shape functions to be defined. Now how do we define them? So we would like to define them at the element level. So to do that at the element level, we play the same game. We go from x1 of the element k, now we will go up to x p plus 1 of the element k. So this is the whole element. It is of size h. Now this element of size h is broken into p equal parts by putting these interior points. Interior points which are located at a distance h by p from the previous point. So this way I can construct these intermediate points. Now we have to define these functions which are 1 at one of the points and 0 at all other points. So can we generalize the definition of the ith shape function that we had done earlier for the cubic and the quadratic to a pth one? Answer is yes. Very simple. We will take the product of I going from 1 to p plus 1. Sorry, j going from 1 to p plus 1 such that j is not equal to I. Product of what? X minus x j for the element k divided by xi of the element k minus xj of the element k. This is for I equal to 1 to up to p plus 1. You see that this definition satisfies all the properties, that is at the node xi of element k, this function has a value 1, at all other nodes it disappears and it is a polynomial of order p or degree p. So this is how we can construct a generic pth order shape function. Okay. Now as far as, so next what we have to do is, we have to do the global to local or the local to global enumeration. That again is very easy. We have the global there, we have the local here. Okay. So it should be quite obvious that this is going to be p into k minus 1 plus I global is equal to the local I. This is for the element k. This is all that we have as far as the global to local enumeration is concerned. Very simple. Provided we put the points in the way I had shown for the p equal to 3 case. Okay. After this, once we have done this, the next job is to do the element calculation. So at the element level, what size element stiffness matrix we will have? So element stiffness matrix will be of size p plus 1 by p plus 1. And the load vector, element load vector is of size p plus 1. Okay. So then I can talk of the ijth entry of the element stiffness matrix. This will be equal to integral from x1 of the element k to x p plus 1 of the element k. This one should be very careful about the limits of this integration. Ea p nj k dx d nik dx. Similarly, fi of the element k is equal to integral x1 of k to x p plus 1 of k f nik dx. That's all. So what we have done is, we have actually given an algorithm or a process, a procedure by which we can now construct the element stiffness matrix and load vectors for an element of any order p. So we are going beyond the p equal to 1, p equal to 2, p equal to 3, we could have any p. Okay. And after that obviously the assembly procedure and so on will follow. That is, assembly from the element will be through where we know that I is equal to P into k minus 1 plus I, and j is equal to P into k minus 1 plus j. So this is how the whole assembly will be done. After we have done the assembly, then we have to apply the boundary conditions. So how do we apply the boundary conditions? For now the approximation of order P. Remember that we are talking of P defined everywhere. Everywhere we have the same P in all the elements. Okay. So boundary conditions. So if you remember, how did we apply the boundary conditions for the linear approximation, that is P equal to 1? So we started off by tackling the Dirichlet boundary condition. What is it for our problem? For our problem we know that u exact at x equal to 0 is equal to u finite element, because they have to be the same, is equal to 0 is equal to the value 0, which means, this means that our u1, the coefficient u1 has to be equal to 0. Fine. So how did we go about enforcing it? So first what we did was, we said that in the global stiffness matrix, K for the first row corresponds to u1. We are going to set all the entries equal to 0 for j is equal to 2, 3 into, yes, you should note that here I have written the total number of unknowns in the problem as n is the number of elements, p is the order of approximation plus 1. One should check that this is what we get. The total number of unknowns, or the degrees of freedom as they are called for the problem, are np plus 1. Okay. So this we are going to do. Then we said that k11 is set equal to 1. Similarly, f1 is set equal to 0. After that, 0 or equal to the value of the applied displacement at the end x equal to 0. But for our problem it is 0. Then we had gone and done the next part, that is, if I had a non-zero value of u1, then I would have to correct the load vector as we had done in the case of the linear approximation, but here it is not so, u1 is equal to 0. So I am going to now set k j1 is equal to 0 for j is equal to 2, 3 up to np plus 1. So this takes care of the Dirichlet boundary condition. So what we have done, the diagonal entry of the first row is set to 1, the load vector entry of the first row is set to 0, all other column entries in the first row are set to 0, and all the first column entries below the first row are also set to 0. That's why we have kj1 is equal to k1j is equal to 0. Okay. Now what about, this is all as far as the Dirichlet boundary conditions are concerned. Then we have the Neumann boundary condition. So what do we know in the Neumann case? If you remember the weak form, we had buv is equal to fv, which is actually equal to integral x is equal to 0 to L fv dx plus p v evaluated at L. So which of our global basis functions are going to be non-zero at the point x equal to L? The answer is simple. It is going to be the np plus 1 global basis function, which has a value 1 at the point x equal to L, and all other basis functions are going to disappear at the point x equal to L. So what do we do in the case of the Neumann boundary conditions? We simply go to the last entry, the last load vector entry that we have, which is f of np plus 1. This is set equal to f np plus 1 plus, to this I am going to add p. So our Neumann boundary conditions are applied. Now we have a system of equations which is of size np plus 1 by np plus 1. We can go use any standard solver which can solve our global problem. K u is equal to f. Solve it, find the values of these coefficients ui. Okay. Now, once we have done it, let us look at some features of this solution. Of the finite element solution. Okay. What are the features? One should note that all these ui's, the coefficients ui in the series representation of UFE, in this case they correspond to the finite element solution evaluated at the point xi. These are the properties of the interpolation functions that we have used, or the basis functions that we have used, that is the Lagrangian functions. One can always construct other families of these shape functions and basis functions for which this is not going to be true. In this case only, in this particular case, these coefficients turn out to be the finite element solution at these nodes or at these points. So we can directly look at the value of these coefficients and say that okay, the solution at this point, the point xi, is equal to this coefficient. So that's a nice thing to have. Okay, now the question is, it is equal to the finite element solution at this point. How good is it? How good is it as compared to the exact solution? Now, as compared to the exact solution, let me make the mesh simple one. I am not going to add all the intermediate points xp plus 1, x 2p plus 1, x 3p plus 1. It turns out, so this will have correspondingly u1, u p plus 1, u 2p plus 1, u 3p plus 1. There is a very interesting property of these solutions which we will see when we do the programming, or one can easily program what I have said till now and see that these things are indeed true, whatever I am going to say. That these u1s, these values for the case EA equal to constant and K is equal to 0. So in this case, that is a problem where there are no axial springs attached to the member and the member has a uniform cross section and the same material everywhere. In that case, there is a very curious thing which happens. It turns out that these values are actually equal to the exact solution at these points. So at, I would say, at the points ip plus 1, exact solution is equal to u finite element at the point ip plus 1, which is equal to u ip plus 1 for I equal to 0, 1, 2 as far as n. This is a very curious property which only the solution to the problem described above has. So the question is, and remember that at other points, at all the interior points, the points lying in the interior of the elements, this is not true. Okay, so let us look at the other cases. In case EA of x is not equal to a constant and k of x and or k of x is not equal to 0, okay, that is either of these is true or both are true. In that case, this is not going to be true. That is, u exact at the point ip plus 1 is not equal to uip plus 1. Remember that in the case of a bar with a variable cross section or with a variable material or a bar with all of these and or these actual strings, this is not going to be true. However, is everything lost? No. It is not going to be true, but this will be very close. To the exact solution. This is a feature of the finite element solution that is again unique to the one-dimensional problem that we are talking about. We will not be able to generalize it to the 2 and 3 dimensions. But anyway, nevertheless, this is a very nice property of the solution. Then the question is, what about derivatives? So finally, what we are interested in are the derivatives. The answer is the following, that let's do a simple problem to answer this question, to see what can be an answer to this question. So let us take a case where the bar is subjected to an end load P equal to 10, a uniformly distributed load Fx is equal to 1, material is EA is equal to 1, K is equal to 0. So we take this bar, and in this case, for this bar, you know that the differential equation will be what we will end up getting, u of x is going to be minus x squared by 2 plus 11x. You can check that u at 0 is equal to 0 because that's what, okay, here we are taking bar of length 1. So length is equal to 1. So in that case, u of x is minus x squared by 2 plus 11x, such that it vanishes at 0 and has derivative of value 10 at the other end, and x equal to 1. So then du by dx for this problem is equal to minus x plus 11. Okay. So now let's try to solve this problem using a 3-element mesh. Okay, 3-element linear mesh. 3 element mesh with linear approximation. So what will I have? This is x1 is equal to 0, x2 is equal to 1 by 3, x3 is equal to 2 by 3, and x4 is equal to 1. And the peak for this approximation is 1. Okay? So what we are saying is that the approximation is piecewise linear. So the derivative of the finite element solution in each element is going to be a constant. So if I plot here on this scale the derivative of the solution, then I will call this number, I am starting here from 10 and I am going up to 11. So what will happen is the exact solution is going to be a straight line which goes from a value of 11 at the point x equal to 0 to a value of 10 at the point x equal to 1. Let me extend this further. Let me now take the midpoint. So this function, this derivative of the exact solution, this is du dx. At this point it has a value of, we have 11 minus x, so it is 10 and 2/3. At this point it has a value of 10 and 1/3. So here it will have a value of 10 and 5/6. Okay. Here it will have a value of 10 and a half, and here it will have a value of 10 and 1/6. And what we see curiously is that if I plot the derivative of the finite element solution, it is going to be like this. So this is DUFE dx. Now what can we see out of this? Okay, this is a picture of the two things, but we can extract some more information out of it. What we see is that the derivative of the finite element solution for this particular problem, for this particular approximation, is exactly equal to the derivative of the exact solution at the, this is the point 1/6, this is the point half, sorry, yeah, and this is the point 5/6. So exactly equal to the derivative of the exact solution at the midpoint of the element. So this was our element 1, this is element 2, this is element 3. So this is a very important property that we have for the derivative of the finite element solution, that is for linear approximations. For this kind of loading that we have taken, it is exactly equal to the derivative of the exact solution at the midpoint of each element. This property is given a name. It is called super convergence. See, even though we have shown it with a very specific example, for linear approximations what we can show is that when we have any other loading, in all those cases, the midpoint turns out to be a point of very good derivative information. That is, the derivative of the finite element solution at the midpoint of the element is very close to the exact solution, in fact closer to the exact solution than the derivative evaluated at any other point in the element. That is why it is called a point of superconvergence. And remember that in this case, the midpoint. Now for p equal to 2, 3, 4, 5, 6, for all these p's, we will have such points existing. These will be called the points of superconvergence, and they will be specific to the interior of the elements. The existence of such points of superconvergence becomes very important when we want to post-process the derivative information. The question is, why do we want to post-process? Because if I look at this here, the finite element solution is doing a terrible job at the inter-element interfaces. Here I know that my derivative should be the same. That is my stress, because my material is the same, should be the same from both directions. But my finite element solution is doing something completely different. It sees a jump. Now the question becomes, how can we use the available information to construct a derivative information which does a much better job than what we have obtained directly? That part, it goes into something called post-processing. That is, we take what we have computed and out of it we get supposedly better information as far as the quantities of interest are concerned. And what will be the ideal case here is, we would like to have to post-process it in such a way that we follow this straight line. Question is, in this problem can we do it? Answer is yes. We will see later on. Not in this lecture. Okay, so let us now look at one more property of the finite element solution in this lecture. This comes from what we have defined as a bilinear form. So this is our weak formulation in terms of the bilinear and the linear forms for the exact solution. Now we know that the finite element solution also satisfies this, but for a particular type of V, such that this is true for V, for all V's which are given as summations of Vi, phi I. For such V's, this is also going to be true. Now for the exact solution, it is true for all admissible V's. So if it is true for all admissible V's for the exact solution, it is going to be true for these V's also. So if I take this set of V's and put it here and take the difference, then I will get du minus ufe comma v is equal to 0 for all v equal to summation of vi phi I. Okay, this property is called orthogonality of the error. Now, till now we have not introduced this term. This error is given by the function Ex, which is equal to u minus u at x minus ufe at x. So it turns out that for all these v's, u minus ufe, if you take the bilinear form of it, it is equal to 0. So how does this property really help us? You see that out of this, we will end up getting a very curious thing. Now, for our problem, can we choose v equal to ufe as a special case? For our problem, the answer is yes. Why? Because ufe is also 0 at the point where we have given the Dirichlet boundary condition and everything else is satisfied. If my ufe was not 0 at the point where the Dirichlet boundary conditions are applied, then this is not going to be true. But for our problem, this is going to be true. So if this is true, then I can also say from what we have done earlier, which means that B UFE is equal to B UFE comma UFE. Now what is this quantity? If I go to the definition of the bilinear form, this is equal to half, not half, there is no half there, EA DUFE dx whole squared dx. Okay. Now this also reminds us of some physical quantity. The physical quantity that it reminds us of is the strain energy of the finite element solution. Okay. And this strain energy, as we can see, is equal to half of B UFE. So we will continue from here in the next lecture, and using this definition of the strain energy of the finite element solution, and similarly the strain energy of the exact solution. Strain energy of the exact solution will be half of B U comma U. Okay. We will talk about how well does the finite element solution approximate the exact solution with respect to the strain energy. Thank you.